Hey everyone, so today we're taking a look at section 3.5, which is over basic differentiation. So our goal is to understand the basic differentiation properties of polynomials. So the first thing that we want to do is we just want to recall the definition of a derivative, which was from our last section. So the derivative, also known as f prime, is defined as the limit as h approaches 0 of f of x plus h minus f of x all over h. And we calculate that using the four-step process that we covered in 3.4. If you look down below at the notation, we do actually have a couple other ways to indicate a derivative that we'll use pretty interchangeably. So the f prime notation, that's what we're used to. We also can use y prime when y is a function of x. We can also use dy dx, which dy dx means the derivative of y with respect to x. So the variables can change depending on what the function is. For example, if I'm using a function with respect to time, I might get like a dy dt. Honestly, going forward, we're going to see the dy dx notation used quite frequently because you can have functions that refer to multiple variables. But all of these we'll use interchangeably throughout the section and going on to the future, so it's nice to introduce them early. The constant function rule. So it says find the derivative of the function f of x equals c, where c is some constant. So we're trying to figure out what is the derivative of a constant. So we're going to use the four-step process. So step one, do f of x plus h. Well, if f of x is c, we're going to replace all the x's with x plus h, but there aren't any, so we're just going to get c. Two, we're going to do f of x plus h minus f of x. Well, this would be c minus c, which equals 0. We're going to do f of x plus h minus f of x all over h, which will be 0 over h, which is 0. And then the fourth step, we're going to take the limit as h approaches 0, f of x plus h minus f of x over h, which is going to be the limit as h approaches 0 of 0, which equals 0. So what this proof is saying here is that the derivative of a constant is 0. So the constant function rule continued. So on the last slide, we showed that the derivative of a constant is 0. And this would make sense. So if we were to look at this picture right here in figure 1, when we take the derivative is also the slope of a function. So what is the slope of a constant? Well, a constant, it has a 0 slope, so it must be 0. And that's why the derivative of a constant is 0. So a couple different ways we can look at it. We can say that f prime of x is 0, y prime is 0, dy dx is 0. And there is another notation right here, and this is worth noting. d dx of c is 0. d dx is kind of like a command. It says take the derivative of the following with respect to x. So they're saying the derivative of c with respect to x is 0. So again, a bunch of notation kind of mixed in with the new concept of just taking the derivative of a constant is 0. On this slide, we might have some of the easiest examples of the whole class. They're asking us to find the derivative of multiple constants. So they're asking, what is the derivative of 3? Well, that would give us f prime of x equals 0. They're asking for y prime, given that y equals negative 1.4. Well, that would give us y prime equals 0. They say if y equals pi, then what is dy dx? So you have to remember pi is not a variable. It's a number. It's 3.14, so on. So its derivative is also going to be 0. So dy dx is 0. And d, they say compute d dx 23. So that's saying what is the derivative of 23 with respect to x? And again, that is 0. all four of these answers are 0 because all four of them are asking us to take the derivative of a constant. The power rule. So the power rule, this is really the meat of this section. This is what we really wanted. The power rule is going to help us take the derivative of anything that is a power function. So a power function is a function of the form f of x equals x to the k, where k is a real number. So it's x raised to the power of something. So examples of power rules, we can have x, because that's x to the 1, x squared, x cubed, and so on. But we can also do like square root of x and the cube root of x and any root of x really, because the square root of x is really x to the 1/2 and the cube root of x is x to the 1/3. So we can convert them to powers, which is something that we're going to do quite frequently, honestly, for the rest of calculus. So before we move on to what the power rule actually is, I want to take a look at something called Pascal's triangle. So, I mean, this isn't actually Pascal's triangle, but an application of it. If I want to look at x plus h to the n, because that's always our first step of taking a derivative, is calculate f of x plus h. So if x plus h is going to be used in a power function, it's going to be x plus h to the n. So if n is 0, anything to the 0 power is 1. To the first power would be x plus h, then x squared plus 2xh plus h squared, and so on. This is something that's very helpful if, they're saying take the derivative of x plus h to the 8th, is I could always look at the 8th row of Pascal's triangle and find it. So if I wanted to, kind of just like a thought experiment, what would happen if I wanted to take the derivative of all of these at the same time? Well, the first thing I would do is calculate f of x plus h, and the next thing I would do is subtract f of x. So if f of x was just, if it was x to the 0, I would be subtracting a 1. If it was x to the 1, I'd be subtracting an x. If it was x squared, I'd be subtracting an x squared, subtracting x cubed, subtracting x to the 4, subtracting x to the 5th, subtracting x to the 6th, and if it's x to the n, I'd be subtracting an x to the n. Why is that important? Well, here the 1's cancel, the x's will cancel, the x squares, x cubes, x to the 4, x to the 5th, x to the 6th. So this would take us to step 2 of our 4-step process. If I already have f of x plus h, subtracting f of x just cancels out the first term. And a rule of thumb that we always talked about is that you wanted to make sure that every term had an h in it after the end of step 2, which if you take a look, everything does. We've got h, 2xh plus h squared, 3x squared h plus 3xh squared plus h cubed. Everything has an h in it. And why is that important? Well, because in step 3 it says divide by h. So if I were to do that, I'd be left with 1. Here I'd have 2x plus h. Here I'd have 3x squared plus 3xh plus h squared. And all of my h's, their powers are just going to be reduced by 1. So I don't think I need to do it for all of them. But you can see that all of the h's, their powers are going down by 1. But the first term will no longer have an h in it. Well, why is that important? Well, as I continue through with my 4-step process, the last step is to plug in 0 for h. So what still has an h in it? Well, it would be all of these guys. All of these guys still have an h, meaning when I plug in 0 for h, they go away. So what am I left with? Well, I'm left with the derivative. So if my function was here x to the 0, I'd be given 0. That was a constant. X to the 1, I'm left with just 1. X squared, I'm left with 2x. X cubed, I'm left with 3x squared. X to the 4, I'm left with 4x cubed. X to the 5, I've got 5x to the 4th. and x to the 6th, I'm left with 6x to the 5. If I was going all the way to x to the n, well, the term I'd be left with is nx to the n minus 1. So you may see a pattern here, and that will be reinforced on our next slide. This slide is talking about the power rule, and this is really building off the Pascal triangle example we saw yesterday, or not yesterday, but on the last slide, where if our function is f of x equals x to the n, then the derivative is f prime of x equals nx to the n minus 1. You can also do it with y prime notation, dy dx notation, but it's going to be equal to the same thing. So if you're feeling a little confused, just wait until our next example because we're going to look at the power rule a lot. Power rule really speeds up taking the derivative because we won't have to do the 4-step process. So in example 2, they're wanting us to take the derivative of several different functions. We've got x to the 5th, x to the 25th, t to the negative 3, and x to the 5/3. All right, so according to our power rule, if I want to take f prime, well, this is a power function, so the 5 is going to come down, and then I decrease the exponent by 1. So it'd be 5x to the 4th. Y prime, and well, y was x to the 25, so that 25 is going to come down, x to the 24. For c, y equals t to the negative 3. So the derivative of y with respect to t, dy dt, is going to be negative 3t. Negative 3 decreased by 1 is negative 4. And then the last one, we're using a fraction. They want us to take the derivative of x to the 5th, or x to the 5/3. I'm going to get 5/3 x. 5/3 minus 1 is really minus 3 over 3. So this would be to the 2/3 power. So hopefully you're seeing that this is a lot faster than if I was trying to plug into a power rule, or not the power rule, but the 4-step process. I mean, A and B would be doable, but they would take us a while. C and D would have been very hard to do. It would have taken us a long, long, long time. But here we can do it in just a matter of minutes. On this slide, they're talking about the constant multiple property, and there is normally a proof that goes along with this in the notes, but it got cut out just for the sake of time. So what they're saying is that if you have a function, f of x equals k times u of x, where the derivative of u exists, then the derivative of f is going to be k times u of x prime. So what they're saying, we're going to see this in a lot of examples, is imagine f of x equals 3x squared. We know what to do if it's just x squared, but what do we do if it's 3x squared? And this property is telling us that if we have a constant multiple, to just completely ignore it and take the derivative of x squared and then multiply by 3. So we're saying that f prime of x equals 3 times 2x to the 1, or 6x. And that's what the constant multiple property is talking about. And we could prove this. If you were to do the 4-step process, you would get this result. But just for the sake of time, they're giving you the property. So example 3, they want us to practice this property a little bit. So in A, they say find the derivative of 4x to the 5th. So the 4 is going to remain 4, and then the exponent is going to come down, 5, and then x to the 4. 4 times 5 is 20, so I'm going to get 20x to the 4th. And that is f prime of x. For B, this looks a little bit harder because this doesn't look like a constant, but you could take out 1/12, and this would be 1/12 t to the 4th. So I haven't done any calculus here. That was just an arithmetic move. You can factor out a 1/12. Now I have a constant, 1/12, times a power function, t to the 4. So to take its derivative, easy as taking the 1/12. The 4 is going to come down, and then it's going to be t cubed. 4 times 1/12 is 1/3, so I'm going to get 1/3 t cubed, and that is dy dt. For C, it's going to be a similar process. The first thing I'm going to do is I'm going to pull on a 1/3. So I'll get 1/3 times 1 over x cubed. Well, that's the same as 1/3 x to the -3. That's an exponent property. But now I have the ability to take the derivative using the power rule. So y prime, the 1/3 will stay there, times -3 x to the -4. 1/3 times -3 is -1 x to the -4. So if you want to, you can put that back in the denominator. I won't make you, because if we're going to take a derivative again, having it as a negative exponent will make it easier. But if you want to, your final answer could be -1 over x to the 4. And that would be y prime. And then the last one, they say compute the derivative of 0.9 over the square root of x with respect to x. So again, I'm going to try to pull this out as a constant. I'm going to get 0.9 times 1 over the square root of x. Well, the square root of x is really x to the 1/2, meaning I can rewrite this as 0.9 x to the -1/2. This will let me use the power rule. So I'm going to get 0.9 times -1/2 x to the -3/2. -1/2 minus 2 over 2 is -3/2. That's where I'm getting the new exponent. And then from here, I can just multiply this together. So I'm going to get -0.45 x to the -3/2. And that would be my final answer. Sum and difference property says that if y equals f of x, which equals u of x plus or minus v of x, then the derivative of f, so f prime of x, will equal u prime of x plus or minus v prime of x. So this is referring to something like f of x equals, let's say, x squared plus 3x. We know that the derivative of x squared exists. We know that the derivative of 3x exists. So if I wanted to take the derivative of f, I would take the derivative of x squared plus the derivative of 3x. And we're going to see that in our next slide. So here we're going to do 4 examples with a sum or difference in them, but you're going to see it works out just like the other problems would. So here, f prime of x, well, it's going to be the derivative of 3x squared, which would be 3 times 2x to the 1, plus the derivative of 2x, which is just 2. And this will give us 6x plus 2. And that's what f prime would be equal to. For y, or not y, for part B, they want us to find y prime when y equals 4 plus 2x cubed minus 3x to the -1. So y prime, the derivative of 4 is 0. The derivative of 2x cubed would be 2 times 3x squared minus the derivative of 3x to the -1. So that -1 is going to come down, x to the -2. So y prime is going to equal 6x squared plus x to the -2. And again, having a negative exponent, in some classes your teacher will fuss at you. In calculus, honestly, most people are going to tell you it's just fine. If you needed to evaluate, so if I wanted to say, well, what would happen if x was 9? You may want to turn that back into 1 over x squared because it's easier to evaluate. But if we're going to have to take another derivative, it's nicer to have it as an exponent and not in a fraction. So that's why I leave it like that. For C, they want us to take the derivative of the square root of w minus 3w. So you just have to remember that this is really y equals w to the 1/2 minus 3w. So dw, or dy dw, is going to be 1/2 w to the -1/2 minus 3. And I'll leave my answer like that. And then for D, there is some cleaning up I need to do here. I'm going to go a little quickly, but the first term, so I'm not taking the derivative yet, d dx, 5/3, so this is going to be 5/3 x to the negative 2. So I'm bringing out the 5/3 and then taking x from the denominator to the numerator, minus 2x to the negative 4. So again, I'm bringing that 2 out front and then taking the x to the 4th to the numerator, which makes it negative, plus 1/9 x cubed. Now it's a lot easier to take the derivative. So the derivative of 5/3 x to the negative 2, that negative 2 is going to drop down, and that'll give me negative 10/3 x to the negative 3, minus, well, it's going to be minus negative 8, so it's really plus 8x to the negative 5, and then plus, the 3 drops down, turning the 1/9 into 1/3 x squared. So that would be my final answer. So example 5, they want to give us a little bit of a real-world example of how we could use calculus. And it says that an object moves along the y-axis, which is marked in feet, so that its position at time x in seconds is f of x equals x cubed minus 6x squared plus 9. And for part A, they say find the instantaneous velocity, or v of x. So if the function is position, the derivative of position is velocity. So position is in feet. The derivative with respect to time would be feet per second, which is velocity. So v of x, which is also f prime of x, it's going to be 3x squared minus 12x plus 9. So for B, it says find the velocity at x equals 2 and at x equals 5. So I'm going to do v of 2, and I'm going to plug in for v of 5. So v of 2, we're going to get 3 times 2 squared minus 12 times 2 plus 9. Well, 2 squared is 4. 3 times 4 is 12. So I'm going to get 12 minus 24 plus 9, which is going to give us negative 3. V of 2 equals negative 3. Let's check for v of 5. So I'm going to get 3 times 5 squared minus 12 times 5 plus 9. So 5 squared is 25 times 3 is 75. So I'm going to get 75 minus 60 plus 9. And that gives me that v of 5 is 24. And if I want to put units, these are feet per second. And then for part C, they're asking us to find the time or times when the velocity is 0. So I'm going to take my velocity function, 3x squared minus 12x plus 9, and set it equal to 0. So I'm going to factor here. I can take on a 3. So I'm going to get x squared minus 4x plus 3 equals 0. So I need to factor x squared minus 4x plus 3. So two numbers that multiply to be positive 3, but add to be negative 4. Well, that's going to be x minus 3 and x minus 1. So that means that x will equal 3 or x equals 1, which means that the velocity is 0 at the 1 second mark and at the 3 second mark. One more example before we're done for the day. It says let f of x equal x to the 4th minus 6x squared plus 10. And then it says find f prime of x. So taking the derivative, f prime of x, that is going to be 4x cubed minus 12x plus 0. And it says find the equation of the tangent line at x equals 1. So to find the equation of a line, I can use y minus y1 equals m times x minus x1. So I know x value, but I don't know y and I don't know m. But if you remember, the derivative is the slope. So if I want to know what the derivative is, or the slope is when x equals 1, let's do f prime of 1, which will give me 4 times 1 cubed minus 12 times 1, which is going to be 4 minus 12, which equals negative 8. So it tells me that my slope is negative 8. And now I need a y value. So remember that y equals f of x. So if I find f of 1, that will give me my y value. So this will be 1 minus 6 plus 10, which will give me 5. So they're saying I'm going to the point 1, 5, and my slope is negative 8. So that's easy enough. It'll be y minus 5 equals negative 8 times x minus 1. And technically you can leave the answer here, but a lot of people like to get it into y equals mx plus b. So if you want to do that, y minus 5 equals negative 8x plus 8. Add 5 to both sides, and you get y equals negative 8x plus 13. And that would be your final answer for B. And then C, they're asking, find the values of x where the tangent line is horizontal. So remember, a horizontal line means that n equals 0, which means that f prime would equal 0. So I'm going to take my derivative and set it equal to 0. So 1 is 4x cubed minus 12x equal to 0. So to factor this, it's easier than you might think. The first thing that can come out is a 4x. And that will give me x squared minus 3 equals 0. So I could have, from the 4x, I could say that x equals 0. That would be one solution. The other one is where x squared minus 3 equals 0, which means that x squared equals 3. So x is plus or minus the square root of 3. So that's a total of 3 answers. I've got x equals 0, x equals negative square root of 3, and x equals positive square root of 3. So this function will have a horizontal slope, or the tangent line will be horizontal at 3 different points on this function. Well, just some closing thoughts. I hope this section made sense. Usually the power rule is a big relief after working on that 4-step process for so long. The 4-step process is very tedious, where you can make a mistake, where the power rule is kind of nice. I always like to think of it as a drop in difficulty. So our next 2 sections, we've got the differential coming up, which will kind of show a few more real-world examples of when I could use a derivative. And then we're going to go into some business applications where we would see calculus used a lot. So hopefully this is making sense. The homework should be posted online. And if you need any help, just make sure you let me know. And if it's making sense, just move on to the next video when it gets posted.